Okay, welcome everyone to today's lecture. We stopped last week here our discussion on option pricing using finite differences. We've seen the binomial model, we've seen the trinomial model, which is a very simple extension of the binomial model, and we've seen Monte Carlo simulation. Monte Carlo simulation being a very elegant but also very simple method to price an option via simulating paths from the underlying stochastic process of the underlying and then plugging those simulated paths into the payout profile of the option in question, and then taking, for example, the average or fitting a normal distribution to those simulated option returns. Now with finite differences we'll take a different approach. It's also in essence a numerical approach that tries to approximate the option price that would analytically be given under the Black-Scholes model. But as you should know by now, for quite a few options, for exotic options that are non-standard, that have a very complex and rather difficult payout profile, Black-Scholes, you cannot solve the Black-Scholes model. You cannot solve for the Black-Scholes differential equation analytically, and you need to find an approximate numerical solution to this problem. So what can you do? Well, you can do Monte Carlo simulation, you can use the binomial model, but something that is even more interesting is finite differences. The basic idea is coming back to the Black-Scholes stochastic partial differential equation. The basic idea here is that all these problems are caused by the fact that we are dealing with a differential equation, an equation that not only includes variables but functions, and we are looking for not a number, but we are looking for an equation for a function as a solution to this differential equation. Now, if all our problems are caused by the fact that you have derivatives of a function, differential quotients within this equation, well, one idea is to simplify the derivatives, the partial derivatives that are part of your partial differential equation. And finite differences do exactly this. You substitute the partial derivatives of your function in the differential equation by taking finite differences. Finite meaning, well, they are finite in differences. It implies that you're substituting the differential quotients by the difference quotients. In German, wir ersetzen normal die Differentialquotienten, sprich die Ableitung, durch Differenzenquotienten, was am Ende einfach nur Steigerungsdreiecke sind. And the idea comes from the notion that the derivative of a function in a point A more or less can of course be approximated by this triangle. And from this you can already see what is needed. You need to find 2 points, usually one left and one right of your point A, where you want to approximate the derivative. So you need this point here, let's call it C, and you need this point, let's call it D, and you need this difference, and you need the difference of f of C and f of D, and then you can calculate the slope of this line here that approximates the derivative. And that's your finite differences. Or that's your finite difference, and then you use finite differences and substitute for the derivatives. So we already know that we need to solve this differential equation, the Black-Scholes differential equation. We have 1, 2, and 3 partial derivatives in here. we have S, we have R, we have the function itself, and we want to solve for this equation with finite differences. For this, again, we need a discrete lattice, ein diskretes Gitter, now with 2 dimensions, time and underlying price. So what happens is, you think of one dimension like this. This is your time. It starts at 0 and it ends at the maturity of the option. And you span your discrete lattice using a second dimension, and this is the underlying price. It could also be 0 and then working up. And for example, one could say 10 euros, 20 euros, 30 euros, 40 euros, and we get a discrete lattice with these points here. And we are approximating the partial derivatives only on this discrete lattice. Not between here, but only between these points. And then we get this lattice, and so on. So let's first span this lattice. We'll take the maturity as the natural endpoint of one dimension, and we need to fix an upper bound for the underlying price. This will be S max. Could be set to 1,000, could be set to 20,000. For most stocks, I would assume it will suffice to fix S max with, say, 300, 400, 500 euros or dollars. That should be enough. Then we have this discrete lattice. It consists of the points S and T, and between these points we have equidistant distances, and these points, as they are equidistant, we say we have 0, delta S, 2 delta S, 3 delta S, and in the end capital M delta S, which is defined to be the maximum upper bound for the underlying price. And we have 0 delta T, 2 delta T, 3 delta T, and so on. And N delta T is defined to be the maturity of the option, capital T. Now, at each point of this discrete lattice, the function value will be f, the option price actually, will be f of I times delta S and j times delta T. So on any point of this lattice, we can observe what the option price should be worth. If you remember the binomial and the trinomial model, actually we had the same thing. We built first the binomial tree for the underlying price, and then we knew what under this binomial tree the option would be worth at maturity. So we had the last row of the last column of this binomial tree, and then we went back and computed and calculated the option prices before that, and recursively we got the option price at the very start. And here we have the same thing. We could also look at the option price if, for example, the underlying price is 20 and we're halfway through here. You would know and you can calculate what the option price should look like. Remaining maturity is now only T over 2, so half of the maturity, and the current stock price would then be 20, for example. Question, what are we looking for? Obviously for something here on this first column, because this column will give you the option prices for different underlying prices, not at maturity. We know this from the payout profile, but we are interested in the current price of the option. So this column here, this will be of most interest to us, because for a given underlying price, we can then simply look up the option price. Okay. Just to simplify the notation, all those points on the discrete lattice will simply be denoted by Fij. So Fij is a point on the discrete lattice, an option price, after I steps up for the underlying price and j steps towards maturity in time. That's Fij. Now, we need to substitute for the partial derivatives. And we do this in the following way. The partial derivative of the option price of f with respect to the underlying price is done in the following way. We now have a discrete change in the underlying price, so we'll put delta s here. And we need to calculate or to approximate the difference the function f takes when s changes by delta s. And with forward difference, we'll do the following. We'll take the current price and move one step forward into time. So this will be, or actually with the underlying price, because now s is the variable that changes. It's a function with respect to s. So we'll start at Fij and we'll move the function one step towards the next underlying price. So we'll have Fi plus 1j minus Fij. In other words, if this is the function, this is the derivative we want to approximate, and this is the point here, we'll take this point, the next point here, and approximate the derivative by this function. In this case, a very coarse approximation, obviously, but nevertheless an approximation. Backward difference, same idea, just start at this point here and use maybe this point. Okay, let's make a new plot. We want to approximate the partial derivative here, and we'll move one step back, maybe this, and then this would be the approximation to the partial derivative. In central symmetric difference, well, that should be clear now. You take one point before and one point after this point, Fij, and you use Fi plus 1j minus Fi minus 1j with 2 steps difference, because now it's a larger triangle. And the same for the option theta. But now you need, because you're now changing the variable t, you're keeping Fi and you're moving forward and backwards in time, so you're changing j, not I. Yeah.
But isn't there just one stock price per point in time? So if I move to a different stock price,
No.
I have to use
No. The lattice assumes that the function f, which is the option pricing function, gives you the option price at any point in time for any current stock price. In reality, of course, we know at which point t in time we are, and we can observe the stock price. So at that point, you can simply look up the one single point on this discrete lattice. But for the function, which is still very general, the function can give you the option price for any combination of a point in time and then current stock price. And this is basically it. You use forward differences, backward differences, or symmetric differences. You substitute the partial derivatives, and then you can calculate the partial differential equation. The second partial derivative in the Weierstrass formula is now approximated, for example, if you use forward differences by this same idea, you simply use an approximation for the derivative. Yeah? So this is fi plus 1j minus 2 fij plus fi minus 1j, and you take the difference in the stock price squared. So that's the second partial derivative. And we now only have the discrete lattice, and we've substituted for the partial derivatives in the Black-Scholes differential equation. What we now need is, again, just like with the regular differential equation, we need to set some boundary conditions. We need somewhere to start. And what do we know? If you think again about this lattice, well, there are some simple things you do know. What values of this function do you know beforehand? Well, you know the strike, yeah, that's a given, but which points of the discrete lattice do you know? Actually, I did a mistake here. You will obviously start here at a stock price of S equal to 0, and this should be 10, 20, 30, and so on. What you do know is this. In many cases, depends on the option, in many cases either for S equal to 0 or S equal to S max, we'll see this later on. Let me put this in parentheses. Either you know what the option is worth if the underlying price hits its maximum or its minimum. Because take, for example, if the stock price is 0, for a European or an American put, for a call, you will let the option expire. You can call for a price that should be above 1, because the strike will be non-zero, and you can buy for 0. You can get it for free on the market. Why should you use the option? So in that case, the price of the option, the worth, the value should be 0. What you also know, and the other way around for a put. Now what you do know is, so this here at the end, you know that in the end, at maturity, the option price should be equal to the payout. Because at that point, no one will pay more or less than the immediate payout the option will guarantee. So you know some boundary values, and you can see this on this slide here. We know that for a European plain vanilla put, FIN, which is, remember, N is the number of steps in time. So at maturity, it's the payout profile. We've already had the same situation with the binomial tree. In the last column of the binomial tree, we know it's a payout profile. We also know that for a plain vanilla put, if the stock price is 0, then we know for a put the maximum payout, and if the stock underlying price reaches its maximum, then the option will pay out 0. So this is actually true. We know that these two lines in one column, these are known. And by setting these according to the outline of the option, and by using the forward, backwards, or symmetric differences, you can solve for the rest of the equation. Now everything's given, and you can solve for the differential equation. For a European plain vanilla call, following holds. Same thing, in the last column we'll have the payout profile. Now for a call, meaning that you can call for a strike, you can call the option, you can call the underlying for a fixed price. If you can buy for the strike, but you can also buy for 0, you can get the underlying for free, then the value of the option is 0. It's worthless. You will let it expire. And the other way around, if you have the maximum, say 300 euros, then you can immediately calculate this payout given the maximum underlying price. Yeah? You need the strike, that's okay. Actually, it should be a capital K here, because it's the strike. Yeah? But you know this. Okay. Now let's first implement the solution for a European plain vanilla put, and we'll use centered symmetric differences and the derivatives to t, so the option thetas will use backward differences. So as a result, we'll get Fij minus 1 divided by the difference in t plus Ri delta s, and so on and so on, and together we'll also use the boundary conditions. Then let j be equal to n, so we'll go back in time together with the boundary conditions, the value Fin minus 1. Just like with the binomial tree, we are going one step back, one column back in time through the letters to reach the first column where the option prices today at t equal to 0 are. This is a function depending on 3 known values, and we can calculate this. So you need to rewrite this a little bit. This is a little bit of algebra, and in the end you get the following explicit scheme. Fij minus 1. This doesn't look very interesting, but remember that you know the last column, and Fij minus 1 is the column before that. So you can calculate Fij. You can calculate the values in a column of this discrete lattice by using values from column j, j, and j. So in other words, you have this column, and you're using, for example, this, and this value to calculate this point, and so on, and you get this column, and you go backwards in time, and finally you have j equal to 0, and this is g equal to 0, and you can look up where is my stock price currently, so this is my option value. This is how the explicit scheme works. Fij minus 1 is just the column before the column in which you have the values already, and as you can see, you need Ai star, Bj star, Cj star. These are given by these expressions, and this can easily be calculated and implemented in MATLAB. So how does it look like? This is a function that gives you a price. Its name, it's uput expl, for a European put with an explicit scheme. We need the starting value of the underlying price S0, the strike RT sigma. We need to fix a maximum stock price, and we need to fix, we haven't talked about this, we need to fix the difference in time, the step length for the time and for the underlying price dimension. Because by setting ds and dt, we determine just how fine this discrete lattice will be. If we set ds to be 10 euros and we set s max equal to 100 euros, we know we only take 10 steps in this dimension underlying price. Same with the time. Because we cannot be sure that s max is a discrete number, it's rounded before that, then ds is s max divided by m. Same with time. This is only a precaution to make sure that we are not entering a maximum price of, say, 255 euros 0.39 or something like that. We'll set up the discrete lattice, the grid, which here is matval zeros, and we are using this linspace here. And the rest is just a very simple direct implementation of the explicit scheme. As you can see, we can set up the boundary conditions. We set up the coefficients a, b, and c. And what we then do is we solve it backwards in time, and we need a double for loop. So we'll go back from column to column up until the first column of the matrix, and we'll start from above, and then for each column we'll go through all the lines. So we'll have this column, and then we calculate this, and this, and this, and this, and finally we get the last one. Okay. Now, this here is the explicit scheme. This calculates f I j minus 1. And finally, we have the first column of our discrete grid. Now, what is the option price? What is the option price? Think again about this discrete lattice here. What is the current option price in the program? Depends on where the current underlying price is. Now, what is the option price if the current underlying price is 20 euros? It would be this value. If the current option underlying price is 10 euros, it would be this point. And you can see that it might be that the current option price is somewhere between 2 points of this discrete lattice. So, for example, if S0 is 15 euros, we need to interpolate between these 2 points here. And this is done in the last line. You take here, you take that S and the first column of our discrete lattice, and you interpolate so that you get the point S0. We'll talk about this later, actually, because what you will do is you have, say, for example, Fij, no, it should be Fi1. Here you have I plus 1, 1. And S0 is somewhere in between. And you will need to interpolate between these 2 points. And then you're just looking where is S0. S0 is here. So you will take this value. And that will be the option price. It's simple to interpolate between 10 and 20. That's 15. We don't need that. But we need to interpolate between the 2 function values for 10 and 20. And this is done in the last line, and this will give you the option price. Frag mal auf Deutsch noch, ist das jedem klar? Sie haben ja dann den Optionspreis für 2 Punkte auf dem diskreten Gitter. Und jetzt machen wir mal eine Annahme. Es könnte ja sein, für 10 ergibt sich S0 gleich 10, ergibt sich ein Optionspreis von 6,5. Für S0 gleich 20 ergibt sich ein Optionspreis von 11,8. Wir wollen aber jetzt, weil wir sehen, der aktuelle Underlying-Preis ist 15 Euro. So. Und dann müssen Sie natürlich irgendwo zwischen 6,5 und 11,8 müssen Sie interpolieren. Und was machen Sie? Sie tragen das einfach in einem Koordinatensystem ab. Also letztlich 10, 6,5. So, ist also hier der Punkt. Und das andere ist 20 mal, sagen wir, 11,8. Und dann machen Sie hier eine Interpolationsgerade und hier ist 15, also ist das hier Ihr Optionspreis, P0. Ja, das macht die Funktion Interpol. Da werden wir später noch drüber reden, aber das ist letztlich eine Interpolationsaufgabe, dass Sie eine Menge an Punkten haben und Sie wollen eine Funktion, idealerweise eine Kurve durch diese Punkte legen. Okay. Let's try this out. We'll first, again, just like in our Monte Carlo simulation examples, we'll use the Black-Scholes pricing formula. This is a European put. It's a plain vanilla put, so there's no need to use finite differences at all because the Black-Scholes formula will be available and you'll have an analytical solution. But nevertheless, we want to see how good is our approximation. How close can it get to the true analytical solution of the Black-Scholes formula? And in this case, the price is 4 euros and 7.6 cents. Let's do the same with our finite differences. And as you can see, we are using, let me just look, the Smax ds dt. Smax delta S delta t. Very small steps in time, only actually 2 in the underlying price. Very coarse, very small discrete grid. And just with very small grid, you can see you get a very good approximation. Black-Scholes price here, same thing, very good approximation with only 2 steps in the underlying price. Now, it doesn't work always. It doesn't always work. As you can see here, let's do the following. We are using the explicit scheme to price this option. This is the price we want, 2.8446. If we only have 2 steps with the underlying price, works quite nicely. If we have 1.5 steps, works quite nicely. If we only have 1 step, well, we get a horribly off result. In German, I would say Fantastilliarden. 10 noch 22. Problem is, the explicit scheme can be numerically unstable. And one way to avoid this is to use an implicit scheme. So we'll use the forward differences and we'll get a slightly different lattice. We'll use fi j plus 1 minus fij and so on and so on. So we'll use forward differences for the option delta and the option theta and the option gamma. This can again be rewritten with ai, bi, ci, and we have now 3 unknowns and only 1 known value. The other 2 unknown values are clearly defined by the boundary conditions. And we'll get a system of linear equations. And this system of linear equation looks like this. It's a triangular matrix. And the rest of the first coefficient matrix is 0. Or the rest are zeros. And the coefficient matrix is triagonal, constant and sparse, sparsam besetzt. Ist in der Numerik ein gängiges Problem, dass Sie häufig Matrizen haben, in denen faktisch nur Nullen drinstehen. Und das eine Problem ist, dass Sie ewig lange rechnen, weil Sie, wenn Sie stupide durchgehen, rechnen Sie immer nur 0 mal 0 plus 0 mal 0 und so weiter und dann Wunder ist 0. Das zweite ist, es macht es nicht besser, weil sie haben eine viel höhere Dimensionalität und dann wird das Problem wirklich auch instabil. And because this is a sparse tri-diagonal matrix, you can use the LR or LU decomposition and we'll show one specific implementation of this implicit scheme in MATLAB. And you can see this here in MATLAB. The function name is actually wrong. It should be, as you can see, we are redefining our previous function. This would be input. So it again gives you the price. You round n, you calculate ds, you round n, you calculate dt, you set up the lattice, same thing. Only thing that is different now, you need A, B, and C. You set up the boundary conditions on the lattice, and then you can do virtually the same. The problem now is you need to solve for the system of linear equations to get those coefficients, those Fij's. And we're doing this here, and this here, as you can see this, we're using the LU decomposition of the matrix. This is done, we have MATML here, yeah, and we are solving for this here. And then afterwards, it's the same thing. We have the first column of the lattice, and you need to interpolate between those two values. Okay. Questions concerning finite differences? I think this is quite simple. You're using the way I've shown this here is quite simple, and you can easily understand the basic idea behind using finite differences. Finite differences are a huge area in numerical analysis and in engineering, because you have partial differential equations everywhere in mechanical engineering, Maschinenbau, and every time you have such a differential equation and you cannot analytically solve this equation, you need to use something fast, something that is as accurate as possible, and then you will resort to finite differences to solve for partial differential equations. Okay. Now, if you have no questions, then let's turn to one of our last topics here in this lecture, interpolation. I guess I only need to ask you, because you're studying mathematics, have you taken a class on numerical analysis, and you've already heard about interpolation? Okay. So this, you can read about this in the Brandi-Mate textbook, but it's included in any textbook on numerical analysis, but you don't need this. You only need the slides here. We're coming back to this problem that we have a function. Ideally, we have the function. Sometimes we only have a set of function values, and we need to approximate the function. And this comes down to the basic problem of having a set of points, and you need to put a curve through these points. Very old, very basic problem in mathematics, in numerical analysis. And we've already seen this. We've seen this on the, actually, 3 slides earlier, because here we needed to interpolate between the two option values on the discrete grid that we have and we needed to find the option price somewhere in between. And obviously we have many. Now if you think about, for example, if we have these, let's assume this is the pricing function. One way, of course, to interpolate between these 2 points here is to use a line. But we could also use a line like this, and we could also use a function that goes like this. And depending on the method we're using for interpolation, we'll get different values here. But we first need to have some idea how to interpolate between points. And this is very interesting. This is first year stuff, second year math, undergraduate stuff at the most. And we've seen this in other places as well. For example, in the Black-Scholes formula, we had an integral. And the integral can be determined using what we call a quadrature, numerical integration, Quadratur, same word in German. But sometimes we need to approximate the integrand and to integrate this accurately and exactly, and this might be more efficient and more accurate. What do I mean? Now, what do you do when you try to numerically compute and calculate an integral? Now, with an integral, you might remember that, for example, if this is your function, what are you doing? You can take points of this function and use those rectangles or trapezoids and sum up the space below these geometric figures. Trapezoids, rectangles, could also use rectangles, and so on. But what you are actually doing is you are taking points on this function, you're taking function values, and in many cases you do a very simple interpolation. So instead of using those rectangles, what you're doing is the following. You're taking these points, you are using an interpolating function that is very simple. Could, for example, let me use a different color. For example, it could look like this. As you can see, this is not exactly the red function, but it's close to it. And if I now told you that this new function here, let me use a little bit darker, this here, this is a polynomial. This is a polynomial function, maybe like x to the fourth plus 8 times x to the third minus 2x squared minus 18. If this is this function, well, anyone at high school can calculate the integral. So interpolation can be used to calculate integrals numerically. You only need this set of function values. You interpolate these points. What you will get is a very simple function for which even a child at school can calculate the integral by hand. And then you'll take the exact integral of the interpolating function as an approximation to the integral you're looking for. Relativ einfache Überlegung, um numerischen Integral zu berechnen, können Sie natürlich mit solchen Riemannschen Flächen, mit Trapezen und allem drum und dran arbeiten, aber viele Verfahren gehen auch einfach her oder bewerten die Integralqualität, die Quadraturqualität, indem sie eine Menge von Funktionswerten nehmen. Die kennen Sie ja, die können Sie ausrechnen. Und dann interpolieren Sie. Sie legen eine andere Funktion durch, die mathematisch besprochen leichter ist, die Sie exakt integrieren können. Beste Beispiel, ein Polynom. Und dann legen Sie ein Polynom durch und dann können Sie ja von so einem Polynom hier 4. 5. Grades, können Sie ja problemlos, können Sie jetzt hier das Integral per Hand ausrechnen. Ne? Das sieht ja hier, Stammfunktion ist dann 4x hoch 3 und so weiter. So, und dann haben Sie das Integral auch numerisch bestimmt. Das ist eine Annäherung. For this reason we need interpolation. If you have had a peek at our outline, you have already seen in gray color the last topic here in this lecture, which will be yield curves and the term structure of interest rates. And this is the foremost important application of interpolation and spline interpolation. We need, or we want to calculate the term structure of interest rates, die Fristigkeitsstruktur der Zinssätze, and for this we need interpolating methods. Because we only have certain interest rates implicitly given from the bonds that are traded on the market, and we need to calculate the term structure of interest rates, so a function that gives you the interest rate for any maturity. Okay, so let's turn to interpolation. under certain circumstances, the function of interest is only known on a discrete grid. This could also be the case. We don't know the function. We only have some function values. Do you know of any example where we have this? Exactly this application, term structure of interest rates. You can only observe the interest rates for those bonds with a certain maturity that are traded on the market. And for example, if you only have bonds with 5, 10, and 30-year maturity, you only have this set of information. You have only this set of data points, and you don't even know the function. If I said to you, please interpolate this function, f of x equal to 5 times exponential function plus 5 square root of pi times, let's say, again, exponential function to the third, you know this function. You might not be able to calculate the integral, you might not be able to plot it, but the easiest way to interpolate, to approximate the function would be to say, okay, let's calculate the function values for f0, f1, f2, f3, and so on, and you only need to plug in those x values into the function, and you will get f0, f1, f2, and so on. In this case of the term structure of interest rate, we don't even know the function. We only have a set of function values. And this is also a very frequent situation, same in all of engineering and physics. You will never know the function behind this phenomenon. You will only observe certain data points, certain measurements in nature. And this is when you need to come up with an interpolating function. In some cases, also, a local approximation suffices. For example, if we have an objective function in a potentially very small environment of a given point. And one example is a Taylor series expansion. You know that Taylor's theorem says that you can approximate this function f by f of x0 plus first derivative times x minus x0 plus half of the second derivative times x minus x0 to the second power squared, and so on. And you know this is an approximation, and this is, even if you take the Taylor series, this is an exact equation in the vicinity of a point, in a small vicinity of a point. And a very simple class of functions that can be used as possible approximations are, of course, polynomials, we know from high school. Now, some general information is in order here. You might have learned this in your introduction to linear algebra. Yeah, linear algebra. That polynomials, just like geometric vectors, just like certain functions, form a linear space. And a linear space has some properties. A linear space, Vektorraum, vector space, linearer Raum, Vektorraum. It allows for the addition, for summing up vectors. So if you take two polynomials, you add them, you get, again, a polynomial. And if you multiply a vector by a scalar, you will get a vector. Same here. If you multiply this polynomial with, say, 5, you will get 5 times this polynomial, again a polynomial. And the third property, which is of interest here, is that a linear space has a basis and it has an infinite number of bases. Linearer Vektorraum hat eine Basis und in der Tat unendlich viele Basen. Und Sie kennen das aus dem R3 oder auch aus dem R2. Sie können zwischen den Basen wechseln und das beliebteste natürlich im Geometrischen ist die Basis 1, 0, 0, 1 oder im dreidimensionalen 1, 0, 0, 0, 1, 0, 0, 0, 1. Dann haben Sie 3 Vektoren und Sie können jeden Vektor darstellen als Linearkombination dieser 3 Vektoren. Okay, does anyone know the simplest basis of a polynomial space? What is the simplest polynomial basis? is what we call the monomial basis, die Monombasis, 1, x, x squared, x3, x to the fourth, and so forth. That's the monomial basis, die Monombasis. Jedes Polynom lässt sich darstellen in der Monomdarstellung, als Linearkombination der Monom. Okay, so polynomials form a vector space. Let Pm x alpha be a polynomial of degree m with coefficient vector alpha. Polynomials are known to be infinitely differentiable, so that they are well suited for both integration and differentiation. As you should probably know, differentiable always requires continuity. Stetigkeit ist dann natürlich gegeben, deswegen spricht man das so schön, also unendlich oft stetig differenzierbar, was jetzt hier trivial ist, weil wir es unendlich oft differenzieren können. Weiß aber jeder. If we now use a polynomial for the approximation of a given function, we need a metric to evaluate, to assess the quality of the approximation. Now suppose we have n values of the function fxi, which we want to approximate. The quality of an approximation using a polynomial can then simply be judged with this following metric. Of course, there are several others one can think of. We minimize the following expression: the sum of the squared differences between the function f and the approximation Pm, but because we only know, usually we only know the function at these points fxi, we can only compare the approximation and the objective function at these points. We'll square the differences, sum them up, and we'll look for a coefficient vector alpha that minimizes this sum of squared errors. You're probably not surprised, because this is the same idea behind ordinary least squares regression analysis in statistics. Eine einfache Fehlerquadratsumme Minimierung, und Sie suchen den Koeffizientenvektor Alpha, der Ihnen diese Fehlerquadratsumme minimiert. By minimizing this metric, we could now search for a suitable polynomial Pm. And you can also use the absolute error, the maximal error, and so on, and use a different metric. Another approach for solving this is to use a linear combination of basis functions, any basis functions actually, to approximate this function, and then the approximating function f will be given by the sum of cj times phi j. Phi j is a basis function, and cj, these are the coefficients. The basis functions could be polynomials, but you could also use other bases. Later we'll see this, that we are using different vectors. But you can use polynomials for a start. And then the approximation task is to look for an optimal set of coefficients cj. Now if the function's approximation is done using least squares, we use n nodes, where the function values are known. For n larger than m, we have too few degrees of freedom when trying to reach an exact approximation with a linear combination. And in that case, well, that's not a big surprise. We have more data than points m, of basis functions m. Then it's the solution of the system of linear equations here. Sum starting from j equal to 1 to m cj phi j at these points xi should be equal to fxi. So the function needs to match, the function values of f need to match those function values of the approximating function at all nodes xi. An allen Stützstellen xi muss die approximierende Funktion den gleichen Wert aufweisen wie die zu approximierende Funktion. And using matrix notation, this is phi times c has to equal y, with y being the function values of the function that needs to be approximated. For n equal to m, this system of linear equations is not solvable, it's overdetermined. Consequently, what happens is, just like in regression analysis, it comes down to ordinary least squares. And we need to look at the sum of these squared residuals. This one is minimized, and you know this from statistics or econometrics. The result is phi transpose times phi together inverted times the transpose of phi times y. Sometimes in statistics you've also seen x' hoch minus 1 x' y. Wenn Sie mit einer Regressionsanalyse mit x und y arbeiten. Das ist das klassische Ergebnis von Gauss, dass Sie hier die Regressionsgrade, die natürlich nicht durch alle Punkte zwingend gehen muss, dass Sie die so legen, dass Sie hier mit x' hoch minus 1 x' y das Ganze ausrechnen. If n is equal to m, the following relationships apply exactly, and this is the case of interpolation. If we have only exactly n equal to m, then this system of linear equation has one solution, and it's unique. And then you can solve for Cj, and this is called interpolation. It's the case that actually, with regression analysis, you have 2 points, and you're looking for a line that goes directly to these 2 points, and then this is obviously this. Then it's unique. If you have a third point, this will never work. Only in one exception, right? And this case here, where you will always have one unique solution, this is called interpolation. So let's do this in MATLAB very shortly. We'll use x data and y data, and as you can see, the function is the log function. Y data is computed by log of x data. So plot x data, y data, and we'll do this with circles. No, and we have 1 point here, 1 point here, 1 point here, 1 point here, and 1 point here. And we'll approximate this. We first use an approximation with a second degree polynomial. So ax squared plus bx plus c, we use the monomial basis, which is 1x and x squared, and we'll use the appropriate function in MATLAB, which is polyfit. P is equal to polyfit using x data and y data and a second degree polynomial. And we'll get these 3 coefficients. And actually it will start with 1x. I think you need to check that if MATLAB starts a polynomial with the highest or the lowest degree monomial. I think this should be the coefficient for 1, this is x, and this is x2. And then let's plot this, and as you can see, the blue line, this is a second degree polynomial used to approximate 1, 2, 3, 4, 5 points. No big surprise, 5 data points, only 3 coefficients. The approximating function, the number of basis points is small. Basis functions is smaller than the number of data points. So what we get is more or less a polynomial regression, not an interpolating function. So what can we do next? We can increase the number of monomial basis functions. We'll do this next here. 1, 2, 3, 4, 5 coefficients. Well, big surprise now, if we use 5 coefficients, if we use a 4 degree polynomial, then it works. At least that we are now able to interpolate those 5 points. But here you can see the next problem. What we are getting here is a function that will oscillate between those points. Okay. Now, this is not a big surprise, but let's look at this a little bit more formally. Now we'll briefly explain interpolation using polynomials. So we're given a set of xi, yi, So endpoints of a function f that is to be interpolated, and we set yi to be equal to f of xi. So yi, those are the function values. Let then Li, being defined in this way, be the Lagrange basis polynomials, and this is the basis of the space of polynomials. Just like the monomial basis, I told you that there are numerous infinite bases for the linear space of polynomials. You will have Chebyshev polynomials, Lagrange polynomials, monomial basis, and so on. In the Lagrange basis polynomials, they are ones of the better knowns. And a very simple result in numerical analysis is that for a set of n data points, there is one unique interpolating polynomial of degree n. Just like we've seen here, 5 points, of degree n minus 1. 5 points, fourth degree polynomial interpolates. The only thing now that is interesting is whether this polynomial here that goes through the 5 points, whether it's unique or if there is another polynomial of the same degree that goes also through these points. Numerical analysis is quite clear, very simple result. This polynomial of degree 4 is unique. Das interpolierende Polynom, das Interpolationspolynom ist eindeutig. Wenn Sie 5 Punkte haben und es ist auch eindeutig, von welchem Grade das ist. Sie können natürlich auch ein 10, also wenn Sie ein Polynom 10. Grades nehmen, klappt es auch, aber sind natürlich interessiert, den Polynomgrad niedrig zu halten. Und das Interpolationspolynom ist eindeutig. Sehr schöner, sehr simpler Beweis. Was Sie machen ist, nehmen wir mal das, was ich gerade gezeigt habe. Okay, let's do this in English again. Let's assume this is P2 and this here is P1. Assume for a moment there are two interpolating polynomials. Then look at P1 minus P2 and call it, let's say, Q. Q is known here, 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 and here. At these points, Q will be 0. And so on. In that case, Q will be a polynomial with 5 zeros of degree 4. And a polynomial of the 4th degree with 5 zeros has to be the 0 polynomial. Then, if Q is 0, P1 minus P2 is 0, meaning P1 is P2. And you've shown that it is unique. Ganz einfacher Beweis. Angenommen, es gäbe ein zweites, dann wählen Sie die Differenz. An den Stützstellen muss diese Differenz 0 sein. Das heißt, die Differenz ist ein Polynom 4. Grades mit 5 Nullstellen und das kann nur das Nullpolynom sein. Also ist Q, diese Differenz 0, P1 minus P2 ist 0, dann ist P1 gleich P2 und das zweite, das existieren könnte, ist wieder das erste, damit ist es eindeutig. Sehr, sehr, sehr simpler Beweis. So the interpolating polynomial is unique. We've just seen this in this case. And it can be represented by Pn is equal to the sum of the Lagrange basis polynomials, and this is why we've chosen the Lagrange basis polynomials in case we're using this basis of the polynomial space. The coefficients are the points yi. Look, we are not using Cj or something like that, but we are using the points y, the function values. And this is very nice, but you can also represent the interpolation polynomial, the interpolating polynomial by a different basis. So let's use this here, this very simple example, 8, 2.5, minus 2, and so on and so on. And we are using polyfit, and we are plotting it. And this is the interpolating polynomial. And as I've told you before with the first example, this is more extreme here. As you can see, this is 1 point and this is 1 point. And the interpolating polynomial goes way down here and it goes up and it oscillates between those 2 points. Whereas we would expect the function, the original function, to look more like this actually. So here, and these areas, in these areas, the interpolating polynomial will oscillate and will probably miss the original objective function by far, by a lot. This is well known in numerical analysis. Never use a polynomial to interpolate points. It will always oscillate, and this problem will be increased and will be worsened by increasing the degree of the polynomial. This works with x squared plus 5x. But if you have more than, let's say, 6 or 7 points, you will need a polynomial of, say, degree 6 or 7, and it will be a mess. So never use it. Why do I show this to you? Well, in the first case, we saw that, well, actually we can start again. Let's take those points here and disregard the blue interpolating polynomials. What is the simplest way to come up with a function that goes through all these points? The simplest way is simply to connect these points. Is this a function? Yeah.
Yes.
Yes, it is a function that is defined section-wise. It will be a function that looks like this. Let's call it g of x will be for x between 1 and 2. It will be a different function between x between 2 and 3, and so on. And you will define the function, the interpolating function, section-wise. Now, this is not a very nice-looking interpolating function. So what will you require? You will require it to be as smooth as possible. So glatt wie möglich, eine glatte Funktion. But what is smooth? What is a smooth function? Smoothness of a function is simply continuity and differentiability. Stetigkeit und Differenzierbarkeit, stetige Differenzierbarkeit, unendlich oft stetig differenzierbar. The more times you can differentiate a function and the resulting derivative will be continuous, that's continuously differentiable, stetig differenzierbar, the more times you can differentiate a function, the smoother the original function will be at this point. Now, we've used lines. Lines in each section. Lines are polynomials. Simplest polynomials, but nevertheless polynomials. Polynomials are infinitely differentiable. So here, this is no problem. In between these points, those lines are infinitely differentiable, even though they don't look very smooth. They are from a calculus point of view. The only problem are those intersecting points. Those intersections here, these points here, where you are gluing 2 points, 2 lines together. And as you can see, for example here, the function is continuous, but it's not differentiable. And by the way, this is always, you can remember this. I just had this problem. I thought, okay, is this function continuous at this intersection? It is, and there is one famous example with which you can remember this. If you've ever asked yourself, maybe you were shown this in your math class, there are some examples of functions that are continuous everywhere, but nowhere differentiable. Überall stetig, nirgendwo differenzierbar. And these functions actually look like this. And they only consist of these breakpoints where the function changes direction dramatically. And if you look at such a function, if you let these points come closer and closer until infinity, you will have a function that only consists of little breakpoints where the function changes direction. It will be continuous everywhere, but nowhere differentiable. So ein pathologisches Beispiel für eine Funktion, die überall stetig, aber nirgendwo differenzierbar ist, eigentlich eine Funktion, die nur aus solchen Knickstellen besteht. It's continuous, but it's not differentiable. So you will need a function that consists of these lines or other functions, and that is continuous but also differentiable, and ideally numerous times differentiable at these breakpoints. And then it will maybe look like this. And so on. And the result will be called a spline. Nennt man auch im Deutschen so, ein Spline. S-P-L-I-N-E. Polynomial spline, where next we'll not continue using lines, but we'll use polynomials of degree 2 and 3 to use as these building blocks for the spline, and will require the resulting function to be twice differentiable, continuously differentiable at those breakpoints. Wenn Sie Polynome zweiten, dritten Grades nehmen, zusammenkleben und die Anforderungen stellen, dass an den letztlich Klebestellen, dass dort die Funktion, die resultiert, zweimal stetig differenzierbar ist das Ergebnis eine zweimal stetig differenzierbare, möglichst glatte Funktion, die schön durch ihre Punkte gleitet, aber nicht oszilliert. And these functions are called splines. It's a very general, a powerful tool in numerical analysis, and it actually is frequently used. I think almost all of you are right now looking at splines. It's used heavily in computer graphics. In computer graphics, to show you animations and pictures that move without having to use so much power from your CPU, your computer will only work with few points. And if it has to show you a graphic, a line, or a curve, or whatever, it will not use all those points that it will show you. It will only use those points that change, and then use an interpolating spline to calculate efficiently the points it will show on your monitor, on your display. Splines and everything that is related to this are used heavily in computer graphics, because you need speed. You need to show it not tomorrow, but you need to show it in a millisecond. And here we're using splines to interpolate a set of points we have, so that the resulting interpolating function will be smooth as possible, and then this is a spline. So we'll next use a different basis of the linear space of polynomials, to be precise, the Chebyshev basis. We'll give Chebyshev supporting nodes, supporting points, Stützstellen, Chebyshev Stützstellen. Our interpolating problem using polynomials will get slightly better, but it will still suffer from the problem that at some point you will have oscillation. And then in the end we'll use splines. Let me just show you how these splines will look like. This is how the properties for the smoothness at the breakpoints, at the nodes, these requirements need to be fulfilled. And then you will have those splines, you will have 4 times n coefficients, and this is how it will look like in the end. Very smooth function that interpolates. It's not a regression analysis, it's not a regression line or curve, but it's an interpolating function that doesn't oscillate, and that is quite smooth. And very simple. It only consists of polynomials of degree up to degree 3. So this is very simple, but you need, you first need to come up with this idea. Okay. Do you have any questions? Because I think it makes more sense to start with spline interpolation next week. So let's stop here at this point where we still need to look at the Chebyshev basis polynomials. Again, we'll see that approximation and interpolation using Chebyshev polynomials helps, but it doesn't help too much. It doesn't solve the problem of oscillation completely. So after that, we'll turn to spline interpolation. And finally, we'll take spline interpolation and apply it to actual data, and we'll calculate the term structure of interest rate based on real market data. You can already access the Excel file and the MATLAB program, and you can try to do this at home on your computer, and you can do the very same thing central banks, just like Deutsche Bundesbank, does on a regular basis. They publish, they calculate, and they publish the term structure of interest rate in their reports. I have to admit, the data I've given to you dates back 10, 15 years. Why? Because back then we had a term structure of interest rates. Yeah? The interest rates in the data, implicitly given in the data, will give you interest rates of up to 5-6% for a maturity of, say, 10 years. Now, it would be interesting to calculate the interest rate right now, but it will only be a flat line a little bit above 0. Yeah? So keep that in mind when calculating the term structure of interest. The data are original. So it's original market data, and you can come up with the term structure of interest rates. Okay, so if you don't have any questions, let's stop here and continue next week. Thank you.